not find any difference because I am a person who never compromises for quality. This is what my nature is. So, after the lunch, we are going to start our session, and with us, is it tomorrow what we do is it possible those who have arrived from the outside, so can you introduce please? The outside, from the outside, please introduce yourself, name and place, university or college name, please. Yeah, this pass.
Manjusha Gandhi, Associate Professor, Yashwantrao Chauhan College of Engineering, Nagpur.
Nanda Prasad Kuswaha, Associate Professor, Tribhuvan University, Nepal, PhD scholar. Thank you very much.
I am visiting you.
Thank you, sir. I am Uday Kumar Khan from Nepal, Tribhuvan University, and I am PhD scholar and fixed point theory. Uday Kumar Khan, yes, sir. Yes, yes. My research in his domain, sir. Yes.
My name is Dilip Kumar Saha from Nepal, Tribhuvan University. I am under PhD scholar under the Ajit Kumar Chaudhary, sir. Yes, sir.
Rahul Mansotra, PhD scholar, University of Delhi. Supervisor, Anuradha Gupta.
Myself, T.K.S. Verma, PhD scholar at NIT Raipur. Dr. Devasis Mishra.
Mohammad Junaid, research scholar, Aligarh Muslim University, and I am a scholar of Dr. Javed Ali.
You know Javed?
Yeah.
Myself, Ahmed Faraz. I am pursuing PhD from Aligarh Muslim University under the supervision of Dr. Javed Ali.
Very good.
My name is Anurag Verma. I am from the Government and PG College, Raipur. Our university is Pandit Ravi Shankar University. My supervisor is Dr. V.P. Tripathi, sir.
Sir, myself, Toshan Srivas. I am research scholar in JGU Bilaspur.
Our university. Okay.
I, Lakshmi Bichal, PhD scholar. My supervisor name Dr. Rashmi Kenwat. I am from Pune University under.
Your supervisor name?
Dr. Rashmi Kenwat.
Okay. Very good.
Namaste everyone.
तो रिश्ते में तो हमारी ग्रैंड
Namaste everyone. My name is Dr. Rashmi Kenwat. Completed my PhD under supervision Dr. P.P. Murthy, and now serving Anantara Pawar College of Engineering, Parvati, Pune. Thank you.
मेरे ख्याल और कोई बचा के बाहर का कल बाकी लोगों को इंटरव्यू कल करेंगे, है ना? टाइम ज़्यादा वेस्ट नहीं करेंगे, थोड़ा दे दीजिए माइक बाकी लोगों से हम बात करेंगे. Thank you. Please, I am not going to disappoint anyone because every day we have something to speak. Okay. So let me introduce Professor Veermani. I have, I think, a long association with Professor Veermani. He is more than my elder brother. Okay. So in that sense also, and for our Department of Mathematics, since my appointment over here 2007, when we have only MPhil students and MSc students along with PhD, but MPhil is more. So those days itself our students used to move to Madras, IIT, Math Science and Ramanujan Institute for their research paper collection or some visits. And he is a man behind that to entertain all our 10 MPhil students. Maybe this no one is right now here, those MPhil students. You visited? Okay, so you visited his house in IIT campus, right? So I think Dhananjay is there, so he will introduce. Actually, I was waiting for Dhananjay, he was a little bit delayed. So he will introduce. So this way, this professor is related to me, that how important personally how important in fixed point theory. So let me say a very fine concept of fixed point theory. You know, after the investigation of fuzzy metric space, it was introduced. Okay, who introduced? You have to tell. Who introduced? No, fuzzy metric space. No, originally who introduced? Veeramani sir has given a tremendous modification in that definition. Right, sir?
Yeah.
Fuzzy metric space.
Not tremendous, some modification.
Yeah. So he has given a modification. What modification? I will request him to answer that and start his session. So that kind of concept which is still going on. Still going on. Whenever some people they refer some other person, and most of the people for a particular cause they have to refer Professor Veeramani. That's true. So that kind of fundamental result he has given. So now let me ask Dr. Dhananjay Gopal to introduce Professor Veeramani and start the lecture.
Yeah, thank you again.
Yeah, thank you, Professor.
So good afternoon to all of you. It's my pleasure to be here and to introduce such a great personality, and indeed thanks to Professor Murthy for this opportunity. As you know that Professor Veeramani retired from IIT Chennai, and he has you can find out in NPTEL his lecture on topology, and as Professor Murthy talk about this concept of fuzzy metric. And in fixed point theory, there is another way that is called the best proximity. So the sir introduced the best proximity, the idea of best proximity, and it is a very geometrical concept. Yeah, along with the curve, of course. But then I found also there is a very interesting, and still there are, maybe later on sir will tell about the idea which the Kerr-Kensar and other Rafa Espinola from Spain, they did many things, and then the renorming recently, the renorming the structure and the related fixed point. Sir told me sometime that there is still the open problem which I don't know whether how to solve it. So it's our pleasure to have here Professor Veeramani sir. So we welcome you for your lecture. Thank you so much.
Again, I think this is there. Again, thank you very much for both Professor Murthy, Professor Dhananjay Gopal, and all faculty members and all the students, research scholars. Yeah, will be more informal, and as Professor Murthy told, I will not go to fuzzy metric space, just I will tell the motivation for that, then we will go to fixed point theory. So, like fuzzy set, we have metric space we know. Matrix X which we are going to discuss, X comma D matrix space we know. It is like distance between X and Y cannot be negative, greater than or equal to 0, equal to 0 if and only if X equal to 0. D of xy need not be equal to D of yx. I come from X to Y one way, return direction I may take another way. But for many interesting results, we need that. We insist that d of xy equal to d of yx, and triangle. In a triangle, sum of two sides is greater than or equal to third side. That's why d of xy less than or equal to d of xz plus d of zy. Then we know that will induce a topology, and we know that again will come back. Then what is fuzzy metric is M for, in fact, Menger, who discussed about probabilistic metric space, then motivated by that, Chromosile and Mikla later they introduced fuzzy metric space and proved Banach contraction theorem. Some kind of So what, according to their thing, that's a like xy elements in the set X. T for like a time, you can think of time, or it is a strength of a machine. That's it has application. Some of our friends from Spain, they have done some application, especially Professor Romagro and others. So this says that like d of xy means one fixed number. It is just a fixed number. It will not change, but we are moving. Now that's what I say, distance between now x and Dhananjay Gopal, now we are very close. Degree of nearness is very close. To which degree we are close? One mean 100%, other than accordingly will, and the earlier thing they allowed 0. That means m of xy comma t allowed to take the value 0 also. But we found that to prove results from analysis, especially to generalize metric space, degree of nearness between x and y 0. That means what? No way they are like, what do you feel? Degree of nearness is 0. Now degree of nearness between x and y is very close. When it will be 1? Only when x equal to y. X equal to y 100%, otherwise depends upon the time, we are moving. So if you move tomorrow or some other time, I will go far away. At time we are close and later we will move. So keeping that in mind, we introduce this is called degree of nearness between x and y with respect to t. We assume that always this is greater than 0, never 0. In the original thing they allowed 0. Then some properties, then in particular m of xy, every metric space will induce a quasi-metric and things like that. Anyhow, just to be told about that, this was introduced when I took my first student, George. In fact, he brought the Banach contraction theorem for quasi-metric space. Then what they use in one of the thing is, like this is very important. Suppose distance between xn plus p tends to 0 as n tends to infinity, p greater than or equal to 1. Can you say that it is a Cauchy sequence? Note that distance between xn and x suffix n plus p tends to 0 as n tends to infinity. Can you say that this such a xn is a Cauchy sequence? Yes or no? Anyone? Especially that's it. Many of you are MSc students, no? Correct? I want. What? Okay. But you have to tell yes or no. Oh, camera may go. Normally my way of I will walk closer to students. Is it a Cauchy sequence? Think over and tell. If you are keep asking me something, do you think that it is a Cauchy sequence? Yes? Okay, I will give one. You are familiar with S1, we are defining a sequence. Sum of n terms. 1 plus 1 by 2 plus 1 by 3 plus 1 by n. N is fixed. S1 means 1, S2 means 1 plus 1 by 2, S3 1 plus 1 by 2 plus 1 by 3 like that. Okay? It's clear? Now what can you say about distance between Sn plus P and Sn? Sum of first n plus P term minus the remaining n term we are subtracting. So this will be equal to 1 upon n plus 1, n plus 2, 1 upon n plus p. What is here p? P does not tend to infinity. P is fixed. It may be 1, 2 or million, but it is fixed. So when n, how many terms are there? P terms. Each term tends to 0, then the sum, like by induction, xn tends to x, yn tends to y, then xn plus yn tends to x plus y, like that by induction. We cannot write for when it is variable. So hence this will be satisfy this condition, whether it is a Cauchy sequence. What will happen if it is a Cauchy sequence? This is a sequence in where? Sequence in R. Every Cauchy sequence in R converges. If this partial sum converges means what? What is the series? Series converges if and only if sequence of partial sum converges. Sn is 1 plus 1 by 2 plus 1 by n. This is a sequence of partial sum of summation 1 upon n, the familiar harmonic series. So we know that that series diverges. In fact, why diverges? Because again, see here itself, instead of p now, take 2n minus s here, then what is this? 1 by n plus 1, 1 by n plus 2, plus 1 by n plus 1. Okay? Is it tends to 0? Now n tends to infinity means 2n also tends to infinity. Now we cannot say that each tends to 0, correct, but sum is not finitely many term. The n also tends to infinity. In fact, this is greater than or equal to first term, greater than or equal to last term. Second term, like every term is greater than or equal to 1 by 2n, n plus n. How many terms are there? N by 2n. It is half. So it cannot be that epsilon is half. We cannot find any n naught. So that norm of Sn minus Sm less than epsilon. So what is important in Cauchy sequence is not the distance between consecutive term or distance between first term, some nth term and n plus 100 term. Distance between xn and xm approaches to 0 as n and m tends to infinity. So this is not a Cauchy sequence. That's why there they assume something what is called T norm. Using that, essentially it will come to like this. Then we modified even the Cauchy sequence, even in fuzzy sense we have to modify, and then we did some result, not in fixed point theory, only in basic result in analysis. Later I did not take any, all the remaining students all from fixed point theory, best proximity point theorem related to function. Not any research level. Okay. Okay, now because as we told, we are going to review some concept from functional analysis, or you call it topology or metric spaces, which we need to understand some of the fixed point theorems. Okay? See, Professor Verenday has given a lot of result related to Banach contraction and that Picard's iteration. Essentially will come back later some other if necessary. All of us, we are familiar with a function from close A. We will assume that A comma B belongs to R, A less than B, to self map. This we call it image of X. For X belongs to the domain, image also belongs to the domain. Such a map, codomain, codomain is same as domain. Such a map we call it self map. you might be familiar, even MSc level, we do this result. Then it has a, then what is the conclusion? There exists f continuous, that is important, continuous map, then there exists this implied, then there exists at least one x in the domain such that fx equal to x. How to prove this? Many of you know. Anyone? That's the interaction, as Professor Murthy and others told, it is not a conference. We try to understand the basic concept, then we can do some meaningful work. Why it is a continuity alone given? The domain is closed and bounded interval. Okay? Even still make it easier, we take even f from using once you prove the same idea. This is continuous. See, what we have is the square 0 to 1. What do you mean by the function has a fixed point? This is the diagonal is y equal to, okay, it is not a rectangle, square you take. X is 0, y 1, 1 1. Here 0 means 0 0. Yeah. So this is y equal to x. Y mean fx. So what do you mean by this function as a fixed point? See, think what will happen? F at defined for every element in the domain. What can be f of 0? Suppose it can be either 0 or greater than 0. Suppose f of 0 is 0, then we are through. We are searching for a point 0 such that x, in this case x is 0. If f of 0 is 0, we are through. Similarly, f of 1 is 1, again we are through. There exists at least one point either 0 or 1, that is fixed. Suppose both are not true, that means what? F at 0 is some positive number, f at 1 is less than that, the function is a continuous function. Using topological idea, not our very advanced topology, very simple, R to R, metric space only. A metric fixed point theorem we are telling, that's why only. What can you say about interval related to? You are familiar, no? What are the connected set in metric space? R is a metric space. D of xy equal to mod x minus y, usual metric. Okay, that will define a topology, forget about that. We can define open set. And then what is the relation between connected set and interval in R? Anyone? Actually MSc student. Intervals are connected and they are the only connected set. Okay, that we can prove using LUB axiom or like that. So, in fact, what is some theorem which we are very familiar? The name is, what is the name of that theorem? Some theorem using that name will not talk about connected or anything. Just will say that some mediate theorem, intermediate value theorem, intermediate value theorem, because ultimately what we want is fx minus, we want to find at least one x for which this is 0, fx at least one x, so that fx equal to x. Okay, now that's this we call it G from where to where? G is a domain is close 0 1 to even R. Okay, we don't About G at 0, F at 0, minus this, okay. What can you say about this? At which point fx is always greater than or equal to g, it is in closed interval 0, 1, x is in closed interval 0, 1, then I mean we will see that at one point it is, because we are assuming that fx is positive this and fx is less than 1, okay, that we do. At one point it is positive, at one point it is negative, then it takes some any value in between. That means we will find an x between f of 0 and f of 1, so that fx is 0. So that is simple exercise you do. Okay. Now, in fact, this is what this will do for any interval, need not be, where we use the, suppose, can we prove this theorem for open interval, even, is it where we use the closeness, I mean a equal to 0, b equal to 1, we need that f of 0 and f of 1. So similarly f of a and f of b, say otherwise continuous image of this is also connected set, image is connected, connected mean again interval, see that should again codomain, it is an interval. If we take a point in between, then there exists a pre-image. So that, okay, this will, you can go through, if you have doubt you can ask later. So you can give also example, f of open interval, it will not work, okay. Next is, it is continuous. What is more important here is, the domain is closed bounded interval, closed interval, that we call it later when you go to functional analysis, what you call interval mean, if we take any point x and y, all the point in between. What is the point in between? X comma y belongs to a, then all, what is the point in between? 1 minus t x plus t time y. It is like telling that at time 0 you are at x, you are travelling, at time 1 you will reach y, okay. So this again should belongs to a for all 0 less than or equal to t less than or equal to 1. If a set has that property, of course we have, if you want you can assume A or R power n, subset of R power n, or any vector space, okay. What we call this? If A has this property, we call it, it is a convex set. So in intervals or convex set. So because when you go to R power n, we don't have interval. See, interval means we define the order relation. See, closed interval a comma b, set of all x in R, say that a less than or equal to x less than or equal to, this order relation is there. If we are in R2 itself, we don't have. More generally any vector space or non-linear space we don't have, but we can define the that we call it convex combination of x and y, set of all. I mean this what even we define this itself for a comma b belongs to a vector space, then we define this is set of all 1 minus t times a plus t times b, say that 0 less than or equal to t less than or equal to 1. So this, because we have addition, scalar multiplication all in a vector space, so define convex set, this is sufficient. In fact you will see that every convex set in a R power n or non-linear space, they are all connected set. In fact it is pathwise connected. Path means, see, that's what I am traveling from xy, any two element. xy belongs to the topological space X. If you don't like topology, take metric space. Okay? Then we should be able to find a continuous function more generally from any closed interval a comma b, a less than b, or in particular enough to consider f from closed interval 0 comma 1 to that vector topological space X, such that at time 0 you are at X, at time 1 you are at Y. There is a continuous function satisfying the condition that f at 0 equal to X, f at 1 equal to Y. Then that we call it a curve or path joining X and Y. If for every pair XY, if there is a path, then we say it is pathwise connected. That's what all the convex set, because not in a, can we define vectors? In a vector space, convex set we can define. Can we talk about connected set in a vector space? Yes or no? Mainly I want from MSc student. Convex set we can define. Closed interval a comma b. Pardon? How we define connected? No separation. A topological space is connected means the only set, the empty set and capital X are both the empty set and X are both open and closed. They are the only sets which are both open and closed. That's a disconnected mean there is a separation. Anything you can assume that even closed 0, anything, even if we can, there is a separation. X equal to A union B, A non-empty, X itself, A is this, B this set, non-empty not equal to X, A is open, A equal to closed interval 0, 1. Is this set is a open set? Yes or no? Capital A equal to closed interval 0 comma 1. Question is it a open set? Yes or no? Pardon? Yes? Oh, yes or no? In R it is not open. So what is your answer? Not open. So what is your answer? You are correct. 100% correct, you got the idea. But still little more. What is our space? Our X is closed interval 0 comma 1 union closed interval 2 comma 3. Our topologic space is not R. R is, we are restricting our space to closed 0 1 union closed interval 2 comma 3. That's in the subspace we call it. Here the sets are open. Each point is an interior point. Suppose if we take closed interval 0 1, 2 comma 3. 1 is 0 is an interior point. Why? Interior point means there should exist a neighborhood. Center at X, radius some epsilon or R. So center at, this is X minus, R positive, okay, X is 0 in this case, X plus R, which is completely contained in our set closed interval 0 1. But open interval 0 minus R, comma 0 plus R is an open set in R. But our topological metric space is not R, closed interval 0 1 union closed interval 2 comma 3. Then we have to talk about, we don't know, our world is capital X, our world is not X, R. So we have to consider what is the open interval here. Open interval, or you call it ball center at X, radius R, mean those elements in our space. We should not go outside our world. So, y in X, as the distance between y and X is less than r. First of all, y should be in x. That means we won't get element from left side. So close interval 0 comma r, x is 0. This will be a open set or neighborhood of 0 in this space. So hence 0 is an interior point. Similarly, even it is here 2 comma mean this side or here 2 some 3 minus epsilon 2, we cannot go beyond 3. So like that. So this okay, at least MSc student you should know some basic thing. Okay. Okay, next question. Exercise is you give proper proof f continuous function from closed interval a comma b to closed interval a comma b, then it has a fixed point. There is at least one. Even it can be every point also identity function fx equal to x. It is not only continuous, it is isometry. What do you call it, isometry? In metric space? Isometry. Distance between fx and fy equal to distance between x comma y. Here fx equal to x, fy equal to y. So distance between fx, fy equal to distance between x. It is an isometry, not only continuous, very strong condition. Still it need not have it has a fixed point provided it is a closed unbounded interval. For example, you take this. Just a bounded is okay, it is not very strong if you feel. Suppose this is standard example. What is this set? It is a convex set. It is an interval. It is closed and what is not there? Bounded is not there. Closed and bounded in R means something we call it compact. It is a closed convex set or closed interval. Will it have a fixed point? Can you give an example from closed interval 1 comma infinity to closed interval 1 comma infinity and give some function which does not have any fixed point? Quite naturally is what? No fixed point means the easiest example is what type of map you can think of. Here you take any x in the domain, close 0, open infinity, you can go right side any, no restriction. See, if you are close interval 0 comma 1, you cannot go beyond 1. Now x anywhere, then you can go anywhere right side. So x should not be equal to fx. So what will be the natural map? Very good. X equal to any translation. Fx equal to x plus 1, x plus 2 or fx equal to x plus a greater than 0. So still it is isometry. Still again this one fx or non-expansive, call it later, will come. It need not have a fixed point. Still more generally, sir, morning all we have seen that distance between x is complete metric space, Banach contraction. Distance between fx, fy, what is that? Less than or equal to k times distance between xy, where 0 less than or equal to strictly less than 1 for all xy. Then it has a fixed point, that too unique. So this is strictly less than. Can you write this? Yes or no? You should be very careful while answering. Can we write k times d of xy because k less than 1? Can you write k of t of xy less than? No. Spelling no is research. Yeah. Why we cannot say? Suppose d of xy is 0, x equal to y. X equal to y means d of xy is 0. Then k times d of xy also 0, whatever may be the k. Then less than d of xy means x equal to d of xy is 0, 0 less than 0. So contradiction. That's why we have to impose the additional condition that x not equal to y. that we call it contractive map. Okay. See, this is for all xy in this with this additional condition x not equal to y. Here also, in fact, this map is a nice map. This satisfies this condition. Again, exercise. Distance between fx, fy strictly less than distance between x comma y for all xy in closed interval 1 comma infinity, x not equal to y. What is fx? I have written. Consider this map. I did not write the map. Consider this map. Fx, I will write. Fx equal to define. Here I have written. Define this f defined as fx equal to, see, x plus 1 by x. That's right, 0 should not be there. Then we cannot write 1 by x. X is positive, you have taken 1. If you want, you take 2, 3, anything. Okay. Then it is not translation now, almost like x plus some positive number. Okay. Then x cannot be equal to fx. Fx means x plus 1 by x, equal to x means 1 by x is 0, 1 by x non-zero. No fixed point. Then exercise, symbol x, that I will give a lot of exercise. D of fx, fy less than distance between xy for all xy in the domain x not equal to y. See, even though not just complete metric space, closed subset of a complete metric space is complete. Okay, closed interval 1 comma infinity is a complete metric space. Domain is complete, but it is a self map. It is not a contraction. But still, what we can get is for each x, we can get that k depends upon xy. K depends upon x not equal to y. We can find a k. I mean, this x not equal to y means we can define d of xy. We can find some fx, fy less than or equal to k depends upon xy times xy. This is less than 1. But what is? It varies. If we vary xy, then x, it may go to infinity also, sorry, 1 also. Okay. So that's why this is the standard example of a complete metric space. You cannot replace contraction by a even contractive. But that case we need a very strong condition, namely compact metric space. F from capital X to capital X, X is a compact metric space. F from X to X map contractive, that means distance between Fx, Fy strictly less than distance between xy, x not equal to y. Then, I mean, essentially we know that x goes to distance between x and tx. It is a continuous function on a compact set attains its minimum. So using that we can prove it. Later we will see. Now, okay, are you MSc student? What is the, when you complete metric space, what are the complete metric spaces you know? Because everywhere we use first complete metric space for Banach contraction theorem or anything, or whatever mornings are discussed. Everywhere we need complete. Because iteratively we define a sequence section, that sequence is a Cauchy sequence, then it converges. No difference between Cauchy sequence and convergent sequence. What are the example you know? Complete metric space. The symbol example. R. I want the proof from one of you. I will give a simple exercise. How you prove? There are many ways. Because R is complete means immediately R power 2, R power n, even any space, LP space, COP, everywhere you will use that R only complete. other some additional, some extra thing. How to prove R is complete? You have to start with a, how to start at least? Let Xn be a, okay, again I will incomplete only, I will give the, we want to prove that R, what is metric? D of xy equal to mod x minus y for all xy belongs to R. We want to prove that this is complete. And in this we can quickly, here there is some nice simple proof. See, which anyone you tell, I will give you, if you know this, if you tell some proof, I will see whether I can give another proof. If you don't tell me, I will not give that, I can give whatever I know. So you tell what proof you know. R is complete, how you will prove? Anyone? You have not seen the proof? Maybe first MSc, BSc now, you are in the third semester, you don't remember? Or start with a Cauchy sequence. Convergence mean what? First start with what is the definition of convergence of a sequence here in R. What do you mean by convergence of a sequence? Give any epsilon. This I normally just for fun I will ask what is epsilon or what is the, you should not ask such a question which is expert will not like. What is the definition of epsilon? Huh? Very small. Can you say it is the closer to zero? What do you mean by closer to zero? Definition. Mathematics we cannot escape. Closer to, I am closer to Mr. Dhananjay Kobal. I cannot, I have to tell, define what is the definition of closer. X belongs to A closer, we have some definition like that. What do you mean by that? It is the smallest, positive, smallest. I wanted that answer to tease you. Is it possible to get a smallest positive number? Whether smallest positive number exists? Huh? No. Positive number, that positive number is such that you give any other positive number, that positive number is less than any other positive number, less than or equal to. It may be equal. Is it possible? There is nothing like, suppose it is a positive number, you call it epsilon or alpha. Alpha is the smallest positive number, mean first alpha positive. Next it is alpha positive, mean what can you say about alpha by 2? Again positive, alpha by 100, alpha by million, everything is positive, nothing like smallest. Smallest positive number, nobody is small in the world. I mean, see, we have a positive number, only thing we know it is greater than 0, that's all. That we call it epsilon, that is depends upon our need, that we call it error. Again this I give some, let us say we want to make a golden ring, nice ring, I want exactly they can measure. Some goldsmith, first day is working, then the total length, or you call it radius, total length becomes 0.9. First day, that means first day he works 0.9. Now you can guess second day, say 0.99. So we call it x1 0.9, x2 0.99, x3 99 like that. Now we know that. Okay. Now what is the error? What is our goal? To reach 1 perfect. The first day if you work, actual value 1, approximate value is 0.9. What is the error? Error is 0.1. Okay. Second day 0.1 like that. So depends upon our need. If you say that our error should not be greater than 0.1, should strictly less than 0.1 means even first day will not work. At least you have to go for second day. Some other engineering, some very important things, aircraft or somewhere, even 0.999 100 times, the error 0.000 something, but still that may cause a damage. Then that case will fix the error is less than 0.00 like that. That's a depends upon our need, we fix epsilon. Epsilon is what? Just a positive number. Epsilon may be 100 also. So, yeah. Suppose your pocket money, say research scholar or MS student, parents are giving pocket money. You will ask pocket money is 0.01 rupees, you will not like, no? At least you tell them, okay, minimum 100 rupees you have to give. There epsilon may be, and it depends upon, just to say that, that's why we fix epsilon is positive. That is more important for engineers than mathematicians. The error. That's why the numerical analysis, anywhere, convergence. And that's what are iterative. We get some distance between xn and the fixed point x naught less than or equal to some k power n divided by 1 minus k. K power n tends to 0. That can be made less than epsilon for suitable large n. Is clear? So, xn converge, that's why we say that first we talk about xn converges to x in R. If and only if, for, please don't avoid to write however small it may be. No restriction, epsilon is positive number. For epsilon, then there exists a stage, what we call it? There exists a stage, that we call it n epsilon. Just to say, if you want you can call it n naught or some other k, such that distance between xn and xn naught less than epsilon for all n greater than or equal to n of epsilon. Is it correct? Cauchy, sorry, this is for Cauchy sequence. Okay, convergence is, first I will define xn Cauchy, if and only if, a conversion will come later. This correct or not correct? Are you familiar? We are not telling that mod xn minus xm less than epsilon for all nm greater than or equal to some stage. We have fixed one n, like telling mod xn minus x naught instead of n naught, because it varies. If we change the epsilon, same n naught will not work. Is correct? Yes or no? This is very, because you can just a triangle inequality, instead of epsilon, you can write epsilon by 2, epsilon positive means epsilon by 2, then we can write xn minus xm less than or equal to xn, xn of epsilon plus xn of epsilon, comma xn. So that's why here xn, xn and xm this, symmetry is there. Each is less than epsilon by 2 means this is true for all n greater than or equal to n naught. This is equivalent, symbol, I mean essentially same thing. Cauchy sequence if and only if this. Now, using this definition of Cauchy sequence, and had you heard about least upper bound axiom? In analysis that is very important. Completeness axiom also they call it. What is LUB axiom? LUB axiom. Not heard? Supremum infimum. But what is the supremum infimum correct? But what is the statement? It is an axiom, not a theorem. Later that's what Professor Murthy also suggested me to discuss about Jones' lemma, because that we are going to use in a fixed point theorem. This also we are going to use completeness. At least basic thing we should know. First lecture today, basic thing, then tomorrow onwards, if time permits, today itself will start or tomorrow. What is? Every closed and bounded set is? Correct. Every closed and bounded set is supremum. But that is LUB axiom. You can prove using that if a non-empty subset of R, non-empty is very important. Non-empty, we cannot just, okay, doesn't matter, empty only I removed, you reduce 1 mark and give the, out of 10, you reduce 1 mark, I have missed non-empty. Non-empty is important. Capital A non-empty subset of R. And it is on, we are going this right side. And you should not keep going like closed one, open infinity, no upper bound. What is upper bound? An element alpha, see again I will recall, A is any non-empty subset of R. A non-empty subset of R, alpha belongs to R. Note that need not be in A, it may be in A, because A is also a subset of R. Alpha belongs to, we don't insist that alpha should be in A. Then alpha is said to be on upper bound for A. When we say if and only if, see A is here, alpha is somewhere, we know the real line. All the x in A should be left side. That means including that, if and only if x less than or equal to alpha for all x in A. Then we say that alpha is an upper bound. Every set will have an upper bound. Any subset of R has an upper bound? No. How to prove? We can say we feel that closed one, open infinity, keep going, go to infinity, hence no upper bound. That is not the proof. For that you need what is called least upper bound axiom. That we call it LUB axiom. What it says is, we have a non-empty subset of R, suppose that non-empty subset has an upper bound, there may be more than one upper bound. In fact, infinitely, alpha is an upper bound means alpha plus 1 also upper bound. X less than or equal to alpha means less than or equal to alpha plus 1, alpha plus 2. In particular, x less than or equal to beta for any beta greater than or equal to alpha. Infinitely many upper bound. Among the upper bound, take the least. So, what is the least upper bound? First of all, it should be an upper bound. Alpha is called least upper bound means first condition, alpha upper bound. Second, beta is an upper bound for A imply alpha less than or equal to beta. Okay. Then what is LUB axiom say is, if a non-empty subset has an upper bound, then it will have least upper bound. That is LUB axiom. Now we can prove that similarly, if a non-empty subset has a lower bound, then it will have greatest lower bound. That we call it infimum, least upper bound, supremum, like that. Okay? This is clear? You feel free, don't worry about fixed point theory, that in between also we will talk about fixed point theory only. But basic thing first be familiar. Is clear? What will happen if you allow empty set? A is a subset of B. Alpha is an upper bound for B. Will it imply alpha is an upper bound for smaller set? Closed one, open interval, closed interval 1 comma 2. 2 is an upper bound. Okay? Anything greater than also upper bound. If you take a subset, closed interval 0 comma half, x belongs to subset means x will be in the larger set. Already larger set itself, every x less than or equal to alpha. I mean subset has an upper bound, superset. larger set has an upper bound means any set subset of that should have an upper bound. Okay. Suppose if you allow empty set,